All right, let's jump right into this explainer. Every time we buy produce, there's this hidden, completely invisible process happening in the soil where it was grown. When we think about agriculture and climate change, our minds usually jump straight to massive tractors, deforestation, or maybe cattle. But there is a silent mechanism happening every single time we feed our crops. It's a fascinating, yet definitely concerning process that we're going to unpack today by looking really closely at two incredibly detailed studies on agricultural ecosystems in Asia.
Here's our roadmap for today. First, the agricultural climate cost. Then, rice versus vegetable fields. After that, what drives the emissions, followed by a simple, colorful solution. And finally, slashing global warming potential. All right, starting off with Section 1, the agricultural climate cost, beyond carbon dioxide. We hear a lot about carbon dioxide, right? But if we look at massive agricultural hubs like China's Tai Lake area, which has this huge history of intense rice farming, we really have to ask ourselves, what else is escaping into the atmosphere? Over the last 30 years, this area has shifted hardcore into vegetable farming to keep up with rising demand, and that has completely rewired the soil chemistry. So, spoiler alert, CO2 is definitely not the only gas we need to be worried about when it comes to heavily fertilized soil. The real hidden culprit here, nitrous oxide, or N2O. Along with nitric oxide, this is a massive and totally overlooked part of the global nitrogen cycle that directly drives global warming. See, when farmers put down synthetic nitrogen fertilizers or organic manure, the microbes in the soil just go into overdrive. They feast on that nitrogen through processes called nitrification and denitrification, and they burp out N2O as a byproduct. And here's the kicker. N2O traps heat in our atmosphere nearly 300 times more effectively than carbon dioxide. 300 times. Moving on to Section 2, rice versus vegetable fields, a tale of two crops. 1,292, that is the staggering amount, in kilograms, of nitrogen fertilizer dumped on just 1 hectare of vegetable fields every single year. Just to put that into perspective for you, standard rice-wheat rotations only get about 430 kilograms. So these vegetable fields are getting absolutely hammered with nitrogen. Honestly, it's way more than the plants can even absorb. And we're not just talking about synthetic urea here. They're also loading the soil with lagoon-stored human manure. And when you combine those intense fertilizer loads with that human manure, you get these explosive emission readings. The data shows massive, towering spikes in nitrous oxide escaping from the fertilized vegetable fields, especially between April and August. Meanwhile, the unfertilized control plots basically flatline at the bottom. It's a crystal clear picture of exactly what happens when you overload soil with way more nitrogen and dissolved carbon than the vegetables can actually take out. The takeaway here is pretty profound. Even though these vegetable farms make up a relatively small slice of the land, only about 18% during the time frame of this study, their extreme chemical density turns them into these massive environmental hotspots. They are completely punching above their weight class when it comes to emitting greenhouse gases, all because of these conventional, super intensive fertilization habits. Okay, Section 3, what drives the emissions? We're calling this the dietary analogy. So, the data brilliantly shows us that these agricultural emissions aren't some slow, steady leak. They are violent, immediate spikes. If you look at the timeline for a rice-wheat rotation, the emissions shoot up instantly right after specific triggers. The exact moment fertilizer is applied, or right after heavy watering or sudden rainfall hits that treated soil, the microbial activity just explodes, and those gases spike straight up into the air. Scientists actually measure this waste using a metric called the direct emission factor, or EFD for short. In plain English, this just tracks exactly what percentage of a farmer's expensive fertilizer is totally wasted by vaporizing into the sky as greenhouse gas. In some of the vegetable seasons where human manure was used, this loss rate for nitrous oxide shot up to 14.5%. That means a huge chunk of the nutrients literally bought to feed the food was instead just actively warming the planet. It's honestly a lot like a really bad diet. If you just blindly force-feed the soil a blanket layer of synthetic nitrogen and organic manure based on a calendar, rather than when the plant is actually hungry, all that excess doesn't just sit there waiting. That human manure adds dissolved organic carbon, which acts like an energy drink for those gas-producing microbes. Add in heavy rainfall that rapidly bumps up soil moisture, creating this perfect low-oxygen playground for the microbes, and bam, that excess nitrogen is lost as greenhouse gas. The researchers even found that when soil temperatures drop below 25 degrees Celsius, these emission rates become hypersensitive to any changes.
All right, moving to section 4, a simple, colorful solution, the leaf color chart.
So how do we fix this without bankrupting farmers? Well, researchers in India compared 2 different methods to find out. On one side, you've got the conventional blanket application. This is the old school way. Farmers just split their fertilizer into 3 equal doses and dump them on the fields at fixed times during the season. It's pretty much just guessing. On the other side, scientists introduced the leaf color chart, or LCC, for real-time management. This acts exactly like a personalized dietary tracker for the plants, feeding them strictly based on their real-time needs instead of following a rigid calendar.
The mechanics of this tool are just brilliant because they're so simple. It's literally an inexpensive piece of plastic with 6 different shades of green, going from yellowish green up to dark green. It's incredibly intuitive. Farmers just walk out into the field once a week, pick the 10 youngest, fully expanded leaves, and hold them up against the chart. If the overall leaf color score drops below a certain threshold, like a 4 out of 6, the crop is visually signaling, hey, I'm hungry for nitrogen. And only then does the farmer apply a top dress of 30 kilograms of urea. If the leaves are dark green, they just skip the fertilizer that week.
And that brings us to section 5, slashing global warming potential. Big results from low tech. To see if this leaf color chart actually worked, researchers didn't just zero in on nitrous oxide. They zoomed out to look at the big picture using a metric called global warming potential, or GWP. Because think about it, flooded rice fields emit methane, and soil can either store or release carbon dioxide. So by looking at the total GWP, the researchers could measure the true overarching climate benefit of giving these crops exactly what they need and absolutely nothing more. The results were pretty mind-blowing. By simply waiting for that color score to drop to a 4 before fertilizing, the environmental savings were massive. We're talking about a 16% drop in nitrous oxide emissions for rice crops and an 18% drop for wheat compared to the old guessing game method. Amazingly, it also knocked down methane emissions in rice by 11%. And maybe the best part? The total carbon fixed in the soil actually went up from 4.89 to 5.54 megagrams of carbon per hectare. Because the plants were healthier and perfectly fed, they pulled more carbon right out of the air. But the absolute crucial takeaway here is this number, 10.5%. A simple, dirt-cheap piece of colored plastic effectively reduced the total global warming potential of that entire rice-wheat cropping system by 10.5%. Just by observing the color of a leaf instead of blindly following a calendar, farmers can pull a massive amount of warming gases right out of the equation. There's a quote from this research that really hits the nail on the head. They note that in many field situations, over 60% of applied nitrogen is lost purely because of a lack of synchrony between plant demand and nitrogen supply. The farmer is literally serving up food when the plant just isn't ready to eat it. Matching that supply to the actual demand completely stops the waste. So this isn't just a win for the environment, it keeps real money in the farmer's pocket because they aren't wasting expensive fertilizer, all while saving the atmosphere from these potent intermediate gases.
The contrast here is just so profound. It really makes you wonder, what other massive, complex climate challenges could we be solving right now with incredibly simple, low-tech observation? We don't always need some billion-dollar technological fix, right? Sometimes we literally just need to learn how to listen to what the leaves are telling us.